Hi, everybody. Good morning. And thank you very much for joining us today in this presentation. My name is Fernando Ayuso. I'm the Director of Data Science and Data Engineering in CKDelta. And I'm here today with my colleague, Alihan Sina. He's a Senior Data Scientist in CKDelta as well. What we want to share with you this morning is what we have done in the last few months to accelerate our GIS pipelines with Apache Sedona. For that, we'll first give you a bit of context on why we are using so much GIS data in CKDelta and why it's so important for us to analyze it in a fast way, and therefore why we had to use something like Sedona. Then we'll get into specific use cases, so you'll get to understand what kind of GIS data we are using and how we are combining it together. And then Alihan will go through the technical implementation, where he'll show you first what Sedona is adding into the picture, what they are adding to speed up this GIS analysis, and then he'll run a demo of code side by side, running GeoPandas and Sedona at the same time. So you'll see the performance improvements. The objective of this session is that after you see this, if you have similar use cases or similar needs, you'll be able to replicate the analysis and the implementation we have done as well. OK, so to understand what CKDelta is doing, I need to talk to you a little bit about what part of a company we are. We are part of the Hutchinson Group. It's a massive conglomerate from Hong Kong that operates in several industries. We are a very big port operator. We have a massive retail operation as well. But most importantly, for the use cases that we are going to cover today, we are a fairly large telco operator as well. We operate in 11 countries in Europe and Asia, and we have a large number of customers, as you can see there. We also have a lot of utilities and infrastructure companies, too. We operate in water, gas, and energy all over Europe and Asia, some in the US as well. The way these, let's say, marketing numbers translate into data in our lakehouse. For example, for the telco data, these 128 million subscribers generate about 26 billion records every single day, events that we combine together with our GIS information. What you see there is a representation, a simplified representation of the cell coverage of Ireland, which is one of the smallest countries we operate in. And in Ireland, we have over 120,000 cells themselves. The way to provide location services with cell data is quite complicated. In every single point in time, you are very likely to be covered by several antennas. Each of those antennas may have several cells. They can be 3G, 4G, 5G, and they overlap in different ways. On top of that, to add for additional complexity, we do have the network team improving the configuration of that network, tweaking the settings, and changing how those antennas overlap each other or how those cells overlap each other. So even if you are not moving, you can be connecting to maybe 10 different cells pretty much at the same time. To add more complexity into the picture, 5G is coming with more and more cells every single day. So this topology changes very often. So if we want to provide the most precise analysis, we have to run our GIS analysis very often with those overlaps. Overall, in our platform, we have over 2 million cells at the moment. When we started working with the telco data, we were looking into SQL tools. We were looking into GIS tools as well. But they were not allowing us to create those end-to-end data pipelines that we needed to run this analysis very often. Especially with the granularity we wanted to get, because we wanted to get ahead of our competitors, so we want to run the analysis as often as we wanted, with the objective of having that speed up and gaining that competitive advantage. What we were able to do was combining Databricks with different Python libraries and user-defined functions to be able to start doing this. And on top of this, we added Sedona later on. In utilities, we realized very soon that it's pretty much everything is GIS data, right? You may have a point in the map that can be a meter, a valve, or a post. We may have any of those kilometers you see in the slides are going to be divided by sections with different connections. It can be a pipe or it can be a cable. And that's hundreds of thousands of the different GIS objects. Similar, which cover areas, similar to the cells that cover part of geography. We may have something similar with primary and secondary stations, or with the number of customers in a geography that the main pipe is going to cover. Just to give you an example, in the UK, in UK Power Networks, which is the energy company that provides energy to London and the southeast of the UK, we have more than 9 million different GIS components. So one of the things to consider when we are talking about utilities is that this is not a native digital industry, right? This is not like an e-commerce website. When you need a new metric there, you just code it, push it to production, and you start recording that metric straight away. Utilities is based in legacy networks. We have those infrastructure implemented decades ago with no IoT devices, no sensors, no connectivity. So what we see is the information is very patchy. Some areas may be very good, some other areas may not be. So what we have learned is that we can use the correlation in, for example, in demand of water, gas, and energy, and learn from the different networks and overlay them with each other. So that's why it's so important for us making the most of this GIS data, and that's why we have to overlay it one on top of the other. Especially because the coverage of, let's say, a distribution of a main water pipe is not going to be the same distribution we get from a primary or secondary station. So they are mismatching, and we have to do a lot of GIS operations to make use of this data. What we saw at the beginning as well was that even the GIS libraries like GeoPandas or Shapley are really good. The speed at which this very intensive analysis was going was not really allowing us to do the analysis we wanted to do. So we were a bit frustrated, right? There was a point that these limits in technology were limiting the kind of analysis we wanted to do, the imagination we wanted to put on them. But fortunately, we found Sedona, and with the speed that we got, we were able to implement a lot more things in a better way. Just to give you some example of the use cases we are implementing and we are using Sedona for. We are working with water leakage. It's a well-known problem in the industry, but it's unsolved. It's not as easy as knowing how much water you pump into the network and how much water is accounted to be consumed by your customers. There is an underground network where getting to know where the water is leaked is very, very difficult. What we know is that if we understand the consumption better, the demand, it's easier to identify where leakage is happening. So we are overlaying that water data with demographics, maps, and point of interest. And we are using the telco data as well to know how many people are in different areas, what's the footfall, to understand that demand better and identify leakage in a more granular way than before. So we are overlapping several different data sets together from the GIS perspective. We are working with customer satisfaction as well, but we are going beyond analyzing the interaction between our customers and the service desk. We are looking into understanding what parts of the network our customers are using to understand how the behavior of that part of the infrastructure is affecting customer satisfaction. That's especially important in telecom. Depending on what's happening in the network, we get different experience. So we can translate that into customer satisfaction. One of the use cases we are the most active at the moment with is about electric vehicles. One of the things we are doing is identifying what are the best locations for electric vehicle charging stations. We do this combining open data sets, EV ownership, car ownership, with, again, mobility data. We get to know where people move around the cities, generalized patterns. We can combine that with that EV ownership, and we can combine that with the maps and point of interest to be quite granular into what are the best places to put those electric vehicle charging stations, which ones are more likely to be successful. The second thing we do with this is translate that into the energy consumption that those new charging stations are going to derive. And what we can do with that is also compare it with the available energy, right? Because not every station will have enough headroom to allow this charging stations to be implemented. So we are looking into that as well. And lastly, supply versus demand. The better we can predict demand, the better we can adapt our supply. That's interesting in the water example I gave you earlier on, the leakage. But if we look into energy as well, the supply can vary nowadays with things like solar panels. So we have to improve how we analyze and predict demand and supply. And here we are overlaying telco, energy, and water data sets with demographics and maps as well, to be very granular. To wrap up, before I hand over to Alihan, I'm going to give you a quick summary of the things we did to start getting into Sedona. So we started working with telco data. Soon after, we looked into utilities as well. We saw that relational databases and VMs in the cloud we were using for Python were not really enough of a solution. So we started using Apache, Spark, and UDF, and we didn't realize all the benefits until we started using Databricks. At that time, we had a reference of what could be done in the market, and until we got Sedona, we didn't realize how quick that could be sped up. We were following the Sedona development until in early 2021, we were able to start using it when it was released. Just to give you some numbers, for an analysis of Voronoi cells we were using in telco, one of our analyses was taking 48 hours. Getting into Databricks, we dropped it to just 2 hours. And with Sedona, it dropped down to just 10 minutes. So fantastic improvement. Hopefully, you start from the Databricks section, not from the slow VMs we had at the moment, but you'll still see a huge improvement in performance. All this with the same size of cluster. Sedona obviously is not perfect. There are some problems. The error messages are not very clear. You have to be very careful what kind of shapes you feed Sedona into. So that was a bit of a delay in the implementation, but after all, it was well worth implementing it. A couple of advantages or benefits we got from this. The first off, the obvious one is in production, something running in 10 minutes is going to have a lower cost. You can run it more often. And secondly, while you are developing this, you're going to be able to iterate over your implementation a lot more if it takes 10 minutes than 48 hours, obviously. And with that, I hand it to Alihan to go through the technical details.
Thanks, Fernando. So Fernando has gone over why we needed Apache Sedona, and I'll go over what Sedona does and how you can start using it. What Sedona does in order to achieve this performance, and how you can start using it in Databricks as soon as possible. So Sedona is basically an extension of PySpark to be able to use GIS objects and functions. It introduces basic building components such as polygons, lines, some special statistics, indices into Spark. So if we were to concentrate on some parts of it, to just break it down, so there are these points, it introduces on the lower level these point RDDs, polygons, rectangles, and these and spatial statistics, some compression and partitioning to be in the lower level, and then exposes these through a new kind of RDD that they call spatial RDD. At this point, you'll be able to use it with Scala and Java, and well, there's also some PySpark RDDs as well, but they're more limited in usage. And on the top level, after this spatial RDDs, there are also spatial ranges, KNN, spatial joins that can be applied after here. And after this level, there's two basic APIs that you can use, which is either SQL API or PySpark API, which generally works quite well with all PySpark pipelines. Sedona introduces around 140 GIS functions. In the documentation, they generally group these in 5. I'll try to do the same thing over here. The first 3 is here. And the first group is the constructors. So there are a lot of different constructors, such as you can create your geometries from WKTs, from points, and from GeoJSON files. There are functions that you can find in most of the GIS modules such as ST distance to calculate distances between objects, ST areas if you want to find out area of polygons, and ST is valid to find out if any of these functions are valid, geometries are valid. Aggregations such as ST envelope, you can aggregate over your Python data frames and then create envelopes around your objects, or union the polygons that's underneath, which is similar to unary union from GeoPandas if you're using it. The fourth one is the predicate functions. So these are any kind of filters that you can apply to your data. And the fifth one isn't really a new like a new group of functions, but you can basically join use all of these functions that we have mentioned just now to optimize your join queries, such as join only where these functions intersect, or join only where the distance between two objects are low. As an example of how a Sedona Sedona code looks like, it is very similar to your run-of-the-mill PySpark function, but there's a little bit of differences generally in when you're reading the data. They have a lot of submodules for you to read data. You can here you see a GeoJSON reader, and then that's read into an RDD, and then there's an adapter that's imported from another submodule in Sedona to convert that into a data frame to enable normal PySpark. And then over here, there's Spark.SQL that's run over this temp view that we have created. And then, of course, the first thing that I always do in Sedona is make sure that I select only the valid geometries, because Sedona tends to fail quite often, as Fernando mentioned before. There are also other, of course, almost for most common shapes that you can use. There's a reader for almost all of them, but in CKDelta we generally use GeoJSON readers, and those have to be GeoJSON sequence files, just to be exact. So so if you write a file as just GeoJSON without mentioning sequence in GeoPandas, for example, it will not work on Sedona. I mentioned before that there are these points, lines, and polygons that are introduced already, but there's also really good interoperability with most common modules such as Shapely and GeoPandas. So what you can start with directly is find the areas where the computation is most expensive in your pipeline, introduce Sedona, and just start reaping benefits, especially like when we started to use this. We had a very complicated data input pipeline, so that was a pain for us to rewrite everything. So we just rewrote the part where the computation was expensive and then extended the pipeline like that. So over here for these points, lines, and polygons, we can declare them in Shapely, and then use Spark that create data frame to directly use them in Spark. And down below you can see that they are now in a Spark format. Now, all of this is interesting, but of course that's not enough to get to the performance level that we just mentioned. And in order to get there, Sedona introduces three main optimizations. Of course, there are a lot of small ones, but the three things that are most important to mention are spatial indexing, spatial partitioning, and also serialization. So spatial indices allow Sedona to access to records faster, and spatial partitioning, of course, in a spatially correlated way. And spatial partitioning allows Sedona to get the closer objects to be in the same workers in your cluster. Of course, when we go from a module like GeoPandas, where it works on a single machine, to a distributed framework, we have to think about this. We have to reduce the amount of traffic between the workers, and Sedona tries to minimize this traffic by analyzing your files beforehand, creating these indices, and then put most of your closer objects together in the same worker. You can use the indexing with R3 and quad tree, and partitioning with quad tree and KBD tree. You can control these finely in the RDD stance, but if you don't you don't have to choose. There are of course defaults in Sedona, and if you don't want to just get into the nitty-gritty of this, Sedona will just do a sampling from your data frames, and then will create the indices based on that and try to create an initial partitioning strategy. Before we get into serialization, let's talk a little bit about why is serialization so important in this context. Mostly we need serialization when we're transferring data between our workers. Spark uses Java serialization by default, which is not really performant. But there's another serialization method that's included in Spark by default, which is cryo, but it is not enabled by default because if you have any kind of new data classes, objects, you have to just introduce them, register them manually one by one. And if you don't do this, normally cryo serialization is supposed to be 20 to 50% better. There are different numbers all over the internet, but this is kind of my, like based on the benchmarks that we did. But if you define it, it's supposed to be 20 to 50% faster. And if you don't just introduce these new data objects, there is going to be security implications and reduced performance. So it's kind of loses its point. So Sedona allows you to introduces these new objects, and it also provides the integration with cryo. So the memory impact is reduced, and it's because we can never truly remove the need to move any kind of objects in between workers, and and then we will, this can be a little bit faster. We can improve performance a bit more. Sedona can use WKB serializer or shape serializer, and these can be configured using Spark configs. And there's a small example over there. It's just like how does, I think this is WKB worker over there, serializer that you can see there. And after now we talked about what the Sedona introduced, let's talk about how we can enable this on Databricks. Luckily, there's really good documentation on Sedona's website that focuses on setting this up on Databricks. So I'd highly recommend going through there if you want to use this. But the version to install for Sedona depends on your Databricks runtime versions. If you're anything after major 10, it's best to use 1.2, which works great, and that's what we're using right now. After you selected your version, now it's time to set up. Now there's some Maven packages that you have to install before using this. The most easiest way to do is just installing the UI, but you cannot benefit from serialization if you do this, because serialization needs to be set up while you're spinning up the cluster. So you can do this for a fast trial, but not recommended for a full benchmarking exercise or a full usage. The better way to do this is installing using init scripts. All of these scripts are also available in the aforementioned documentation on Sedona's website if you want to have a look into there. After you go and set these init scripts up, it's of course the time to register these to your cluster, and then put up the Spark and then put the correct Spark configs in order to use that. To talk a little bit about Spark configs, so there are roughly 3 and 1 optional one that I use almost always. So the first one is SQL extensions. So there's Sedona visualization extensions and SQL extensions. As soon as you put this in, you'll be able to use Sedona in your SQL notebooks. The second and third is first declaring that you want to use cryo serialization, and the third one is introducing the Sedona's extensions to cryo to be able to use in the data objects. The fourth one is not on the recommended list, but I see whenever I try to use this in in the pipeline, I always see that the RPC message side errors, since the GIS objects tend to be much larger than normal rows, there tends to be problems in there. So increasing maximum size to 1024 is better than Databricks' default 512. After the Spark configs, you're now ready to use these in SQL notebooks, but to use this in PySpark, you need to first install the PyPy with the correct version, of course, the version that you have installed from your Maven packages. And after that, there's the Sedona registrator function that is that you can get from one of the submodules, and then extend your Spark session, and everything that we have mentioned before will be available. When you see the true down there, when you don't see true, you'll probably see something like JVM sub package not found. So if you see that, it's better to go back and check out some of the earlier steps if you see that. Oh, let's go to a small demo. Hope everything works as intended. We're here, but I'm not really sure if you can see that. All right, I will just go to the backups. To do that, we have. All right, so just like a small performance comparison. So in here, we were supposed to have 2 data files, one of them with 3G and 4G cell shapes that we use in one of our countries, with 75,000 cells in both. The cluster was supposed to be run with a standard DSV2 with 2 workers, and the task would be to just find the overlapping cells. Now, if you run both of these notebooks side by side, I'll go into them normally, but I don't think you could see my notebook, so I had to come back to this. But generally, just with like a small task like this is just one operation. The performance increase that you've seen over there had over 10 times more cells than this. No, 20 times more cells than this in both of the files. And we had to go through about 20 different operations to get the final result. So just one operation with small number of cells, the increase is about 2 times, 2.5 times mostly. But of course, we are using 2 workers as well. There's a little bit cost, but the performance benefit increases with the complexity of your job. And so this would be the notebook that we would have seen if the demo worked. And so import GeoPandas, read both of the files, then use GPD Overlay. It is very straightforward. There's nothing complicated. There's almost no complicated optimizations that we do in either of those. So it's just a straightforward read the file, overlay, show the head. And if you were to show the same with Sedona, so with Sedona, of course, there's a little bit of setup that we need to do. We need to import several objects from the submodules of Sedona, like GeoJSON reader, Sedona registrator to extend the Spark session, the adapter to be able to get the spatial RDD into a spatial data frame, which you don't have to always do if you just want to work with the RDD. And then extend the Spark session using in the third line, and we have to reintroduce re-register the Spark context because the Spark session has changed. The set system property, I find that could be necessary if you have large GeoJSON files with a lot of additional information in there, which sometimes causes problems. Setting the global character set to UTF-8 generally works great. And then similar to the code example that we went over, we'd read the GeoJSON reader to the RDD, and then convert that to a data frame. And over here, so we have now 2 tables. There's a cross join between 2 tables. Select the ID fields and use st-intersects to get the IDs for only the objects that intersect between 2 tables. And then, of course, since this is a Spark data frame, you have to call some action to display the result. To wrap it up. For conclusion, just a couple of key takeaways. So Apache Sedona extends Spark to be able to use GIS functions and objects. There's very minimal changes required for migration from the most common GIS tools. There's a very easy setup on Databricks on the Sedona's documentation, and we have seen significant performance upgrades in every pipeline that we have introduced it to. And I think we have 2 minutes if you have any questions. Yeah.
And so like one parcel might not be valid. Have you had to deal with data sanitization problems in your data?
Well, yes, but I think for those ones we tend to use something like, we still keep using Spark UDFs. So so there's different parts of the pipelines, and for those there's still we use Spark UDFs, and like we get the GeoPandas data, like the objects, GeoPandas objects, and then benchmark and then broadcast them to all of the workers, and then in the UDFs refer them inside the apply in pandas functions, just read them through there, and then because as far as I know, I haven't checked in the recent ones, but there wasn't a way to actually go into the polygons and fix them inside there. Like you can add buffers to the objects if you have any kind of like closing issues or small issues like that, but you have like large issues with like a lot of null datas. I feel like we still go back to Spark UDFs in order to fix them. Any other questions? All right. Well, we'll be around for a bit more if you have any more questions, and feel free to connect with us if you want to ask us anything more about this. Thank you all for coming.